And here's where we're moving now. We're going to move to this thing called two-way ANOVA. All right, so we're going to call this two-way analysis of variance. Two-way ANOVA. Now, if you can't see the board, let me know, and we'll try to make sure everything is okay. And these next few moments that we're going to write down is going to seem really like, okay, this is just too theoretical or too it doesn't involve any problems. But just trust me on it. Even if you can't really understand as we're going through and writing down, we're going to need what we write down now when we actually go through and do a problem in Excel. Okay, so again, it may not seem like you can sink your teeth into the concepts at the present time, but you just have to trust me and just know that it's going to make sense a little bit later. Let's say definition. Two-way ANOVA. Two-way ANOVA is a statistical technique that analyzes the effect of, lo and behold, two factors on measured data at the same time. Okay? So two-way ANOVA is a statistical technique that analyzes the effect of two factors on measured data at the same time. Quite clearly, one-way ANOVA was looking at just the effect of one factor. But when we did one-way ANOVA, we didn't even bother saying what the factor was, right? So for example, we had the example Wendy's, Burger King, blah, 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 blah. We didn't even have to really say that that factor was restaurants, right? Because that's the only thing we were looking at anyway, right? So that factor is going to be the general idea or the category title in a sense. See, we just said Wendy's, blah, 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 blah. Now, when we stated 8 sub 1, we said not all mu restaurants are equal, right? So saying restaurants is, in a sense, saying that's the factor, right? But see, this time it's going to be a little bit more important that we say what the factors are as we do the analysis, okay? So in terms of the picture, in terms of the data, I'm going to do this. In terms of the picture, let me show you this picture. And so we're kind of on page 451-ish. It's kind of a summation. It really kind of starts on page 453 if you think about it. And thank goodness that we're not going to have to do all this mathematics, because on page 455, 456, that's all the mathematics that's involved in the two-way ANOVA, but Excel is going to help us do that. So in terms of the picture, here's how the data is going to be presented. So I'm going to say data presentation. Data presentation. Here's how it's going to look. You're going to have factor B. You're going to have factor B here. Now, factor B is going to have, let's say, column 1, data. Column 2, data. So forth and so on. Column 3. I don't know how many, right? They keep going and going to, Taco Bell, Wendy's, or whatever, right? Going that way, right? And, so whenever we talk about factor B, and we're going to write this in a second, it's only going to involve the columns. You say, well, that's kind of strange because, see, before that was the only factor. So why would that be sort of like secondary? Why wouldn't that be factor A? Well, just in statistics, we just always call it, in a two-way analysis, the column factor B. That's it. But then we're going to have factor A. We're going to have factor A, which is going to be looking at, we're going to call the rows, row 1. So in addition to, so this is the data how we typically have been looking at it, just this factor and then just one row of data. Well, see, here in two-way analysis, now you're going to have row 2, then data, 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 right? And it could go row 3, row 4, right? And notice here, for example, this factor A, so that's restaurants, for example. This factor A could be another way of grouping how we're going to measure the data, okay? And we're going to take a look at an actual example in a second, but I at least want to show you how the data is going to look. So when we say factor A, this is going to be another category heading, just like restaurants was right here, and then we listed the restaurants. This is going to be a different factor with another heading, and these are going to be like row 1, row 2 is going to sort of be like the subcategories in the actual row column heading in a sense. So you're going to have this going on, and so you're going to look at, try to analyze the data, trying to say, well, for example, drive-through serving times or advertising strategies. Not only are you going to see what kind of effect this has on this data right here, you're also now going to look at the influence that this has, this column here, or I'm sorry, this row or this category has on the same data. Okay, so again, I know it's kind of, you can't really sink your teeth into it, but at least I want to show you how the data is going to look. And when we put it in Excel, Excel is going to help us. So that's the good thing about two-way ANOVA. We won't have to do anything by hand. Excel is just going to pump out the results. Now let's try to get an understanding of what these factors mean. All right, so I'm going to say definition. And as I clarified earlier, factor B, I'm going to start with factor B since that's what we kind of used to, shows the analysis of column categories. You know, columns are straight up and down, right? Analysis of column categories on the data. Okay, so that's like, oh, I don't know, I'm going to say example, column 1, column 2, you know, etc. Okay, so the only thing is just trying to get you to remember that factor B going this way, factor B going this way, and we're going to say definition. So that's factor B. Factor A shows the analysis of row, R-O-W, row categories on the data. I just say example, like row 1, right? And so when you're given the data, you have to figure out what factor A is, and then the things that make it up. So row 1, row 2, etc. Okay? All right, so now let's get general test flow. How does this two-way ANOVA work? All right, so I've let you finish writing that down at the bottom. So let's get kind of a strategy of attack for how to solve the problem. And you want to really make sure you're taking good notes because on the exam, so let's see, quiz 2 is next week. So that could deal with anything on Tukey, anything on one-way ANOVA and Tukey, or what we go over on today. And since there's no mathematics involved in this right here, then the only way I could deal with this on a quiz is if I gave you like some kind of output and had you to analyze it, right? So we're going to figure out that in this course, it's not just about solving the math. You're going to have to keep struggling with the English, you know, trying to understand it and how to interpret it or how to analyze it. That's the name of the course, data analysis, how to analyze it. So you're going to have to sharpen your skills about how to write it and make some sense out of it. So I just wanted to give you a heads up in terms of how the quiz could sort of come here. But we're going to go over this today. So, all right, so let's say general test flow. Okay, if you're looking at how to solve a two-way ANOVA, what's the general kind of pathway or the general flow chart in a sense to help us figure out how to solve this? So here's a general broad brush stroke. We're going to say you will perform either one test or three tests. Boom, bottom line. Bottom line. It's almost like when we looked at one-way ANOVA, you said when you get here, you stop, you don't do Tukey, you do Tukey, right? Well, in this test, the overall idea is that, boom, I give you a problem. And you will either perform one test and stop and go to the next problem, or you will perform three tests, stop and go to the next problem. Never two. It's either one or three. And you'll kind of see how that flows on, all right? But I just want to give you a general idea about the test just in general. All right, so let's look at step one. Let's say step one. Okay, so make sure you have really good notes when you're dealing with this. So when you take the exam, you can sort of look at your notes and kind of see what's going on. We're going to call this the test for interaction. The test for interaction. The test for interaction. All right. Now let's define this. Let's say definition. The test for interaction determines if there is interplay between the two factors. Okay, so this says the test for interaction determines if there is interplay between the two factors as it relates to the data. Okay. Now, again, you can't really see this unless you see a set of data, but when, for example, we're going to look at an example later with the drive-through serving times again, and we had restaurants, and we're going to find out that the next category is going to be something like, I don't know, location or something like that. And so if there is interaction between restaurant factor B and location factor A, if there's what's called interaction, then what that means is the results of drive-through study time depends, the restaurant location, the drive-through serving times of a certain location depends on where you are, right? And if there is interaction between the two factors, that's going to hinder me from looking at restaurants' impacts on the drive-through serving times individually, and then, I don't know, location individually, right? Again, you won't be able to kind of see this until we kind of do a problem, but you're going to have to test for interaction first. Now, when we say test for interaction, all that simply means is on the Excel, so when we actually do this, here is what, when you do the step one, your 8 sub 0 is going to look like. Step one, when you solve the problem, you always need to show me what 8 sub 0 looks like and 8 sub 1 looks like in step one. Okay, so this is an interaction definition, but this is kind of what I expect to see here. We'll say the null hypothesis is there is no interaction. There is no interaction between the two factors, factor A and factor B. And again, basically, so think about drive-through serving times. If I'm looking at different areas and I'm looking at different restaurants, if it's low, if the drive-through serving times are low in this location and low in this location, then I go to the next restaurant, they're both low. Okay, that makes sense. I go to another location, oh, it's high now. When I go to this other location, I expect for it to be high, right? When I say that there's interaction, that means it's low here, high here. We go to the other location, they switch, right? So you kind of see like that crossing of effect. They have to kind of act the same as you sort of go across, right? So that's a general idea. And we'll look at some data later. The H1 says there is interaction. There is interaction between the two factors. There is interaction between the two factors. Now, how do we determine this? How do we determine this interaction in terms of the math, right? You can't just wonder if there's interaction. Well, that's okay. That's okay. On Excel results, this is how you know. On the Excel results, compare F test to crit or cutoff. When Excel gives the cutoff, it gives it as F crit, but it's the same thing, like critical value. We call it F cutoff, that's fine. Compare F test to F crit for interaction. Okay, so when we actually do a problem, make sure you have this visible so we can sort of know how to proceed. But when we put the information, put the data in Excel and look at the results, we're immediately going to be able to figure out what's going on with interaction, the F test, and the F crit. Now, once you find out this information, the interaction has its own diagram, and all the diagram is still going to be an F distribution, right? So the F crit will go here, and the F test is going to be kind of wherever, and it's going to be the same thing. If the F test is on this side, we're going to accept. If it's going to be on this side, we're going to reject. Okay, but we're only looking at the values for interaction in that particular problem, right? Now, clearly, if the F test is on this side, except X is 0, there is no interaction between the two factors. If it's on this side, we're going to conclude that there is interaction between two factors. See, this accept or reject is telling you whether to accept or reject X of 0, right? So if you reject X of 0, that means that this one is in play. If there is interaction between the two factors, so let me say this. Let me say this. If we reject X of 0, in other words, if we prove that there was interaction, if we reject X of 0, then we conclude that, see, if you prove an interaction, then we conclude that we may not continue with analyzing. Okay, if we reject X of 0 for X of 0 in this step for interaction, then we conclude that we may not continue with analyzing the data. Your solution should use, okay, so this says we may not continue with analyzing the data. Your solution should use the word depends. Okay, so we'll see what happens if we end up in that situation. Stop and move to the next problem. Okay. So the test for interaction is the very first thing that you do in any two-way problem. Okay? And depending on what these results are, if we reject a sub 0, then we conclude that pretty much the problem is done, is finished. We just have to figure out how to write that final sentence. When we use the final sentence, we just have to make sure we use the word depends in our estimation. Okay? So again, we're going to look at a problem today. I can't remember if we reject here, but so somebody will need to remind me. If we never get to the point where we use the word depends, let me know, and I'll try to figure out how we would word it in the case that we did reject. Okay, so this is a situation where in the entire two-way ANOVA problem, I've only done one step, but after doing this one step, the problem is done. I don't need to move to steps 2 and 3. Okay, so remember we said this test you'll either do one step or 3 steps. Yes. Okay, so this is where you only deal with one step of the problem. Proving interaction proves that you can't analyze any further. All right. Okay. So now let's keep going. Let's keep going. Let's get to step 1 and 3. Again, you're going to have these handy when we do the problem in just a few minutes. And so all interaction means is that there's some interplay between factor A and factor B. Let's look at steps 2 and 3. Now notice here, if you get to this point, what do I mean if you get to this point? That means if when you were testing for interaction, you accepted H sub 0, right? If you accept H sub 0, that says you have just proven, oh wow, there is no interaction, right? If there is no interaction, that means I proceed to the next steps in the problem. But when I proceed to the next steps in the problem, I must do both of those steps. You see that? See? So if you get to this point, and let me say parentheses, except H sub 0, because that's the only way you can get to this point, you must do both of these steps. It's either one or none. All in, like you're not in at all, and then you just go totally in, right? You're swimming on the beach, just, toes in a little bit. No, I don't really like, past step 1. Well, hey, let's just go, and you end up all the way in the deep end, right? So it's either step 1, then or step 2 and 3. Okay, so that's why I said steps 2 and 3 together, because once you get here, you must continue on. But let's at least look at step 2 right now and see what's going on. Step 2, we're going to say the test for the factor A effect. The test for the factor A effect. Okay. Now, each one of these steps has its own H sub 0, H sub 1. Each one, right? So we're going to say definition. As you may expect, the factor A test determines if there is an effect of row categories. So the factor A test determines if there is an effect of row categories on the data. Now remember the diagram we did before, we had B up here, factor A, these right here. So this is in a sense trying to test what effect does this category have on the data itself, all right? Now, each one of these steps, now we're in step 2 here, the test of the factor A effect, it has its own 8 sub 0, 8 sub 1, right? So you're either going to look at one set of 8 sub 0, 8 sub 1s, or 3 sets of them, right? Now here is how 8 sub 0 looks in this case here. I hate that this board is so small. I have to sort of keep erasing. But yes.
What does the definition say? I'm sorry, I can't read it.
Oh, okay. So this says the factor A test determines if there is an effect of row categories on the data. Effect of row categories on the data. All right. Now, in terms of how 8 sub 0 looks, it's going to look like this. Well, in fact, in one way ANOVA, we're used to writing things a certain way. So we're going to say mu row 1 equals mu row 2 equals mu row 3 equals dot, 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 depending on how many rows you have, right? So, you know, depending on what the row category heading is, if it's location, for example, then this would be mu, the first location, mu, the second location, right? And we're going to try to see what effect these rows have on the data. And 8 sub 1 is going to simply say, not all mu, let's say whatever this row category is, are equal. Okay? Not all mu row categories or row category, whatever the row category title is, are equal. Now, in the book, I'm just going to rewrite 8 sub 1. I'm going to rewrite 8 sub 1 to say it this way. 8 sub 1 says this. Essentially, 8 sub 1 says there is a factor A effect. This is just another way of stating 8 sub 1 a different way. So if the problem says determine if there is a factor A effect, in order for there to be a factor A effect, that simply means that you have to reject 8 sub 0, right? If you reject 8 sub 0, that means that, there is a factor A effect. One of these here has a not equal sign inside of it in terms of our 8 sub 1. Now where it is, I don't know. But if you see the terminology, is there a factor A effect, that's simply saying that if you get to this step in the process, you're looking to see whether you accept this or reject this. If you reject 8 sub 0, that means that there is a factor A effect. Okay? Now let's say solution. Let's figure out how to write the solution here. And again, we're doing this without data, so, you know, yes. Yes.
I'm sorry, what does it say after not all blank are equal?
Yeah, so this says mu, you know, the symbol mu here.
Yeah.
And then as a subscript, it says row category.
Okay,
So,
thank you.
Right. So say, for example, if, I don't know, let's say if factor A was ethnicity or something, right? So that would be the row category. So then this would be something like mu African American, mu Latino American, mu Caucasian American, right? So you have the category, the general category, and then these are like sort of the subheadings up under it in a sense. Okay. Now I'm going to say solution here. How do you write your solution? Let's say make a final statement make a final statement. And I know you guys are doing a bunch of writing this morning, but that's okay. Make a final statement regarding factor A on the data. If you reject, okay, so this says make a final statement regarding factor A on the data. If you reject H sub 0, we use the terms, and you already know this, at least one pair, and I don't know, you tell me. When you reject, we need to use the term at least one pair, and what other word? What other word do we normally use when we reject? Yes, is this really?
Significant.
Very good, very good, very good. So, I mean, you're going to see that the two-way ANOVA process is really, once you get through interaction, the two-way ANOVA process or two-way ANOVA is really two separate one-way ANOVAs, if you want to think about it like that. But the only way I can get to analyzing the two separate one-way ANOVAs is I've got to be able to cross the threshold of interaction first. All right? And then find the rows that are significantly different. And I'll let you guess which process we use to figure out which ones they're different. Right? I won't even write it. So make a final statement regarding factor A on the data. If you reject H sub 0, just keep going with, how you're going. And if you accept, then you're basically saying all mu rows are basically equal. All right. Now, once we get to this point in the lesson today, when we start looking at actual data, an actual problem, as I mentioned before, you are going to use Tukey down here to figure out which rows are significantly different, but it's going to be based on a different Q statistic. So at some point today, we are going to need our Q tables. And let's go ahead and tell you this. So make sure you write this down. And this is pretty much page, so we just went through page 458, if you're kind of following me here. And it's saying the exact same thing that we just said. So look at page 458. The bottom is interaction present. Then our cell mess, blah, 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 blah. Cell means plot. We're going to come back to that to see how we do that on Excel. So we're on page 463 right now. Look at page 463. Yeah. And even on the top of page 464, it shows like the diagram there, right? All right. Well, once you get down here and have to figure out which rows are significantly different, we're going to use the Tukey, Q-U-K-E-Y, but our Q is going to be different. So I'm going to go ahead and write this so you can have a reference for this. We're going to use the Q chart, but this time we're going to use R. This R is going to be the number of rows. And then we're going to use R times K times N minus 1 for a certain alpha. So this R is going to be the number of rows. The K is going to be the number of columns. N minus 1, like the number of what's going to be called replicates within the actual data itself, right? So we may have 9, 9, 9, 9, 9, 9, right? So this is just what we're going to use in factor A if we have to get to figure out which rows are different. So at least write this down so you can kind of refer to it. Okay, and finally, step 3. I could have done these as handouts, but I think it's better if you kind of write it like in your own So we're at step 3 now, and you probably could do this on your own. The test for the factor B effect. The test for the factor B effect. Okay, definition. This test determines if there is an effect, so I'm using the word effect of column categories. Okay, this test determines if there is an effect of column categories as they relate to the data. All right. Now it has its own set of null and alternative hypothesis. Looks like this, as you may expect. H sub 0, you have mu. So this time, see, we're looking at columns now. See, so this is the test for the factor B effect. All right. So we have mu column 1 equals mu column 2 equals mu column 3, and so forth and so on. See, depends on how many columns you have, right? If it's restaurants, then mu McDonald's, mu Wendy's, or whatever there. H sub 1 says not all mu column category. So if this is Wendy's, Taco Bell, whatever, then the category is restaurants. See, not all mu, and then whatever the category of the columns are, you just put that right here, are equal, right? So now, just like we said before with factor A, we can restate it in terms of H1. I can also restate H1 this way. There is a factor B effect. Okay, so this says right here, there is a factor B effect. So in other words, if I reject H sub 0 and show that not all columns are equal in a sense, then essentially I'm saying that there is a factor B effect. So if it says determine if there is a factor B effect, assuming I've gotten past the interaction prohibition in a sense, or pass code or whatever, then once I get here, I'm trying to decide whether I'm going to accept or reject this. Okay. Now I didn't write the other one, but all of these, thankfully, see, it's an ANOVA test. All of these, thankfully, have to do with comparing an F test to an F crit. I didn't write that for factor A, but it's going to have its own F test, F crit, F test, F crit. So we're going to see all these different results for F test compared to F crit. So all of them then also have their own diagram, right? I didn't draw this diagram for factor A, but essentially I'm going to analyze one of these diagrams or 3 of these diagrams in the problem. Now let's say solution. And then that'll be it for doing this stuff without any data. But I'm glad we're kind of doing this so you can sort of see how we would proceed. Solution. Make a final statement make a final statement regarding, okay, so this says make a final statement regarding factor B on the data. I'm not going to start over because it mimics exactly what we said for factor A. Accept or reject x of naught or x of 0. You know, if you reject, use at least one pair or significant, blah, 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 blah. I'm not going to rewrite that here. Accept or reject x of naught. If you reject x of 0, find columns that are significantly, okay, so this says accept or reject x of 0. If you reject x of 0, find the columns that are significantly different. And the good thing about when we get down here, so far we've only been introduced to one Tukey table, but for two-way ANOVA, it's two separate Tukey worksheets. And I'm going to give them to you. One is going to say something like Tukey for factor A, and then Tukey for factor B. And only thing you're going to need to fill in that data is the output from the two-way ANOVA and your Q table. And so for Tukey here, if you get to it, we're going to use, when you look in the Q table, it's going to be different than what we just said. So for columns, when we're doing the column analysis, we're going to use Q. Then here is going to be K. See, before it was an R right here. So K, which is the number of columns you have. And then this is the same thing right here. R times K times N minus 1 for a certain alpha level. Now, I was looking over, yes, what is
What is that before the K?
Oh,
Is that like
it's a capital Q.
Oh, okay.
Yeah. Sorry, I won't write my Q's kind of different, kind of weird.
Okay.
Yeah, sorry. I was noticing when I was grading your lab from last week, some of us are having problems using the Q table. Like some of us were getting values like I forget what it was, 3 point something. But for one way, I want you to go back and make sure you know how to get the values on the Q. Now the first thing is make sure you're looking at the right side of the table, right? Because you have 0.05 or 0.01. If you're using the Q table that I put on Blackboard, I think it gives both of those numbers there together, right? But either way, make sure you're looking at the right side of the table, and then make sure your arrangement of, well, last week it was like K times Q and K times N minus 1 or something like that, whatever it was for last week. But you want to make sure you practice putting in the right Q value, because if you put in the wrong Q value, that's going to affect your output. Whether the means are significantly different or not. Okay? If you look on page 4, and we'll take a break right before we do this problem so we can gear up for this. Page 468. Look at 468 and 469. And again, don't worry about whether you can understand like MS and all that stuff. Excel is going to help us with that. But in that box, those two boxes, you see where it says critical range equals, oh God, I don't know if you can see that. It's really tiny. That's a Q. Don't worry about the U there. But you see like it has like a little R, then N times C times N minus 1 is really tiny. Well, their C is our K. We're calling, whatever they're calling C, we're calling K. Then on page 469, that's a Q, and then that's like a K, then R times K times N minus 1. So that's kind of where that's coming from. The only thing that's saying is just make sure you're looking at the right value on your Q table, okay? And you may or may not even get there, but if you ended up rejecting H naught when you go to these steps, then that's what they're going to be looking for.